Can we sing the cup song?
No cup song.
I'm joking.
7.5 Newtonian Gravitation. We'll start with Newton's law of universal gravitation, where F equals G_m_m over r squared. This is the force between two masses.
Colin, test with the face.
Okay, like I'm not ready.
Hey, did I leave my Forte charger in here?
I haven't seen it.
Okay.
Colin, it's Reinerman's class.
Thanks.
Or at least it was there in second period.
Ah, okay, that means it must be there.
Pretty well.
Where is your second period?
Wait, was it today?
Yes, today.
Okay. Yeah, it's
Oh, I'm tired. That's sad.
Forget it, trigger actually.
Colin, $1 tomorrow, please.
And he is in the class.
You're even like in the army soldiers, just walking around.
I get bored walking back and forth in front of the whiteboard. He seems to be controlling my Sugar Son's chatter a little bit. I'm practicing in my other classes.
What does it mean axis along a line?
Axis. The shortest line between two, so a straight line between the two masses.
So right now there is a line of gravitational force between you and me. But since
You're gravitationally attracted to each other.
You're
but
gravitationally
since
attracted to
I'm not
everything on
like
in
a
the
sumo
universe.
wrestler, it doesn't actually affect you. And also because
No, you're not. That's not enough.
and also because Earth is affecting us.
If you watch that one episode of Family Guy where like Peter he grew so much gravitational mass that everything around him
Started to float into orbit.
That's
Yeah.
so funny.
Yeah. My favorite one is where they open a cookie store and that lady comes in.
Do you collect cards from Orbital? Oh, which one? That's losing higher. I know. Thank you for putting me off by 7 minutes. I time how much when I eat it.
That's so bad.
Okay, so wait. How far is this gravitational force pulling from? Because am I pulling that folder over there? Am I pulling someone on the opposite side of the Earth?
You're
On the
pulling
opposite side of the
everything in the universe.
It's just so small because the distance is so large
Oh,
that
yeah,
it
I
can affect
I
you
understand
for near infinity.
Right now,
The furthest star in the universe is pulling on you.
And I'm pulling on it.
And you're pulling on it.
That's why that
I'm
With
not
the
stuck.
same amount of force.
that's why that one little pair of yours is sticking up.
I'm not stuck in here with you. You're stuck in here with me.
That's Newton's third law. Okay, so this G is a G gravitational constant. It's not like little g. Little g depends on what planet you're on or how far away from the planet you are. Big G is a universal constant. All the little things at the end, this newtons, meters squared, kilograms squared, that's a unit. Don't try to put values in for that. That would be silly.
I'm sorry, that sounds like two raptors. Big G and little G.
The gravitational force is always attractive, so it's always going to be attracting other mass to it. It will not repel like magnets, you know how they attract and then repel depending on which way they're pointing. Gravitational force is always attractive.
Well, okay, wait, I have a question now.
Yes.
So if everything has gravitational pull on it, then what about the two like opposite ends of a magnet? Are they still like attracted to each other?
They are still attracted to each other, but it's not gravitational force. That's magnetic force. It's a different type.
I mean, the same ones. I mean, yeah.
They're
like when they
repelling
repel.
each other. Yeah.
But there is a known tiny force of gravity, but it's the magnetational force.
Magnetic force is stronger.
Yeah. Magnetation.
Also,
Magnetation.
do your organs have gravitational pull on every other organ?
Well, yeah, but it's really, really small.
That's so, like, and I hate to be, like, weird, but that's really trippy.
The cup or your holding are attractive.
Yes.
Okay, guys, stop. I can
All right. So that means that the force on mass 1 due to mass 2 is the same as the force on mass 2 due to force 1 to mass 1. This is force 2 to 1, 1 to 2, equal and opposite Newton's third law. The force between them is the same. Yes.
Okay, so what? Wait, are they saying that the masses are the same?
No, they're saying that the forces are the same.
What?
Because even opposite reaction, like, even though, say, me and an elephant are pushing on each other, right, even though we have different masses, there's still the same amount of force.
The same force between them.
Yeah.
Wait,
It's just that you're going to move before the elephant does because you have less mass, so you're going to have more acceleration.
Unless I am a sumo wrestler.
Wait,
In which
is
case-
gravitation different?
Hmm?
Is the gravitation different?
No, the gravitational force is the same.
Okay.
It's the same. It's the masses are different, so the accelerations different. All right, universal gravitation. The gravitational force exerted by a uniform sphere, so think about an Earth, on a particle outside the sphere is the same as the force exerted if the entire mass of the sphere were concentrated in its center. This very confusing paragraph means that you can treat large objects such as the Earth as a single point. So even though all that mass has to take up some space, imagine that it's just a single point, like a gravitational point that has this field around it. That allows us to simplify a lot of problems. This is called Gauss's law, and you learn a lot more about Gauss's law in like electricity stuff. So when you take physics 2 in college, they'll talk about that.
I thought this was physics, not chemistry. Why are we learning about gas laws?
Because it's science. Gauss was a person, and you see Gauss in all
I'm
this.
sure there was an unfortunate guy named Gas.
Yeah. You know.
And the only reason I really bring Gauss up here is because you are going to see him again. Doesn't matter what science you take, you're going to see him again. It just means that you can treat it as a particle with the field.
This guy's going to overachieve or fancy pants, huh?
Okay, this is a big example. I just can't like visualize it. Can you draw a picture or something?
Sure. All this is saying is that even though this picture right here is the Earth, a really terrible Earth, I have to draw that over. I'm sorry.
Is it making a sonic noise?
There we go.
I don't think it's making a sonic noise.
It always makes a sonic noise.
Okay, so here's the Earth, and it's just saying that instead of this being an object, think of it as a single point that has a field around it. So that if that object is here or here or here, you're just going to instead treat it like all the mass is just like one little tiny point. That way you don't have to worry about like, is it inside the Earth, is it outside the Earth? If it's inside the Earth, some of the mass is going to be on the outside of it, some is going to be on the inside of it. So just worry about what's on the inside. It just simplifies our problems a lot. It shouldn't mess you up in any sort of way. You just treat your problems the same. It's just something that I want to kind of introduce because when you get to physics 2, here's a charge, and it's in a metal sphere. There's some things that you do with Gauss where it actually has a different force due to Q here than it does here, sort of thing. It's a little weird. But that's stuff like physics 2
So you're
that
trying to solve
you'll do
physics
that.
2 on us.
Yeah. So that's where Gauss is going to come back in. But all you need to know is that pretend the Earth is not an Earth. It is actually a point that has as much mass as the Earth. It's a black hole. It's the size of the Earth. It is a mass. But that's Gauss's laws taking these Gaussian surfaces and things like that. It gets very complicated, and we will not talk about that. But this should not affect any of your math at all. It's an interesting concept. Okay, so this gravitational constant, this 6.67 times 10 to the negative 11, was first experimented with and found by Henry Cavendish, which was in 1798, which I believe you guys talk about in chemistry for whatever reason. Yes? No?
It does sound familiar.
No. Okay. Well, basically, he took a spinny ball thing and gave it, basically, it was free to move, and then he put some more massive, like lead-type balls on the outside, and he measured how much it moved when he put them there. Because it's gravitationally attracted, right? So it's going to make it spin. So, like, he'd turn it this way, and it would, be attracted to it. And he measured this using a laser in a mirror to figure out exactly how much it was moving, so he could figure out the speed that it's moving and calculate this g.
Oh, really? Lasers in 1798?
Well, he had a light source. It was, probably not a high-tech laser like you're thinking.
Or maybe a box and a light bulb.
Or maybe a laser.
Or maybe a radioactive isotope.
So you're going to hear the word Cavendish at some point, I'm sure. I don't think you'll hear it on the AP test, but, he's famous for this experiment. There's actually some experimental, lab equipment I've seen like this, but I don't think we have any of that stuff. I haven't been able to find at least
Did you check the
full
supply
sets.
closet?
Yes, I did. All right, so using this equation, this F equals GMM over R squared, we're going to actually figure out G. So, how do we find weight? What's the equation for weight?
W equals W.
Force equals mass times gravity. Is this mass times gravity, is this weight any different from this equation?
No.
The gravitational attraction between two masses. No, it's not. So we can set these two things equal to each other. If this is the mass of U, right, the U versus the Earth, which is actually like that, there we go. So U goes away, mass of U, and you're left with the gravitational pull of the Earth. And anything at the surface of the Earth is going to equal the gravitational constant times the mass of the Earth over the radius of the Earth, because it's on the surface of the Earth. So you could find the gravitational acceleration if you went at some sort of altitude above the Earth. So for instance, if you wanted to find what G would be if you're out here in a satellite.
It's a banana satellite.
All right. So you're going to have the radius of the Earth plus the height of the satellite. So when you do these things, sometimes it'll only give the altitude of the satellite, and you need to make sure that you're adding that to the radius of the satellite because we're treating the Earth as a single point, that Gauss surface thing. Now, sometimes it'll ask you, what's the gravitational attraction between the Earth and the Moon? In that case, you can assume that the total distance they give you is between the centers of those two objects. But for a satellite or anything that's orbiting the Earth, usually they'll only give you the height or the altitude, so you need to include that radius as well. So if you wanted to look at those equations, this one would change into and this one would change into so make sure you add them before you square them. If you notice here, we have different altitudes. As you increase your altitude, you're decreasing the gravitational acceleration. It's just an interesting table. You don't need to write it down. Here is gravitational potential energy. Potential energy is actually a negative because the further away you go, the less force you feel. So the closer you are, the more of a force you're going to feel, so the more potential energy you have. So they actually talk about this as a negative, which is kind of strange, but as long as you're consistent with that negative, you should be fine. So basically they're saying the further away you are, the less potential energy you have because you don't have a lot of pull on you. So not going to have as much energy. You're not going to accelerate as quickly towards it because your force is less. So they say infinitely far away. If this goes up to like a really, really large number, it's going to be very small on top versus it. Basically, no potential fusion. So that's why they make it negative. It makes it kind of confusing in some of the problems, but you should be okay as long as you just are consistent. Notice that the only thing that's different between the force and the potential energy is this r squared.
When you say the Earth's surface, do they mean water?
Yes. Okay, here's the equation for escape speed. This equation is escape speed, so this allows you to get off of the planet or the moon or whatever it is, a black hole. It's going to be 2gm, whatever it is you're orbiting, over r.
Wait, so that determines how much you need to get
How much velocity you need to get out of orbit, to escape orbit.
Okay.
To escape the attractional pole, the gravitational pole. Notice that the velocity is independent of the mass of the actual object. So if you're launching a satellite versus launching like a giant space rocket, right, or an asteroid, the mass of the object doesn't really matter. The only thing that matters is the mass of the planet that you're trying to escape and how far away from that planet you're trying to escape. In this case it says E, that's just, they're talking about Earth in this case. But it could be anything. It doesn't have to be Earth. These are some escape speeds needed to escape planets in our solar system. You can see that the bigger the planet is, more likely the more massive the planet is, the higher velocity you need. Notice that's in kilometers a second, not meters per second. So really fast. Just interesting, that's in your book. All right, here's some equations I want you to have. The bottom one we already have on the board. We also have velocity in general is going to be the square root of g, whatever you're orbiting, the mass of whatever you're orbiting, over r. And the amount of time it takes to make one revolution, which is period, capital T, is going to be 2 pi, the square root of the distance between the two objects, over the mass that you're orbiting. I'm going to put mass at the center, C for center here. And this is mass at the center. Because it's always based on what you're orbiting, not what you are. It doesn't matter how big your mass is or how small your mass is. It's not affected in these equations. This ME up here is meaning Earth, but it can, again, it's whatever you're orbiting. It could be a moon, it could be a sun.
Wait, so what's M again?
And this mass,
Yeah, so didn't you just say mass doesn't matter?
the
No,
mass
mass
of you
bending.
does not matter. Whatever's escaping. The mass that you're orbiting does. That's why I put C's on it.